Hello, my name is Theofilos Petsios, and today I'm going to presenting to you some of the work we have been doing over the past months at Columbia University on automated domain-independent detection of algorithmic complexity vulnerabilities. And this is joint work with Jason Zhao, Angelus Keramitis, and Sumanjana. So before going into the details of this work, let me take a step back and talk a bit about complexity vulnerabilities and complexity bugs. So complexity bugs occur due to differences between the average and worst case complexities of certain algorithms or algorithm implementations. So this could be CPU or memory usage or disk space. And these bugs turn into a vulnerability in cases where they're actually user controlled, in which cases they could lead into exploitability or denial of service scenarios. And actually, such instances appear again and again in the wild. So perhaps you remember the Stack Overflow website takedown from a simple regex. So that was taken down for 30 minutes. Or we have had several cases of hash table collisions in PHP taking down PHP applications. And there have been instances in the academic world where complexity attacks are combined to exploit file system races or to come up with cover timing challenges in the kernel. And just this year, for instance, there was just this month, sorry, in Node.js, there was a complexity vulnerability that resulted in increased CPU usage. And the reason these problems occur again and again is, of course, that the detection of such bugs is generally a hard problem because complexity vulnerabilities are heavily dependent on the application logic. And also, it's not only the algorithmic worst case, but in several cases, the implementation really matters. So minor changes in implementation drastically affect the performance. And think about the very well-known example of quicksort, where just a pivot selection can drastically affect the performance of the overall implementation. So it is often the case that theoretical analysis is not trivial. For instance, for regexes, there has been a lot of related work trying to analyze and come up with a theoretical formulation about the properties of how do you get a regular expression denial of service due to complexity issues. And of course, this becomes even harder if you take into account the implementation. As a result, modern tools predominantly require some expert knowledge. But let's draw a bit from a well-known case of quicksort to see what are our goals for this work. So basically, quicksort has a difference in the complexity of the average and the worst case. So from n log n, you have a worst case, a quadratic complexity. And that's a big difference, of course. So in the case of the Stack Overflow website, the matching of the regex was actually quadratic, and it still took the entire website down. So the question we wanted to ask was, how do we reason about the effectiveness of a given implementation with respect to its complexity vulnerabilities without actually diving into the details of the implementation itself? So how would we be able to test this in a domain-agnostic manner? And of course, one natural choice for this was to turn into evolutionary testing. So evolutionary testing is a very well-known technique which offers domain-independent test input generation. And it has shown to perform really well in gray box settings where you don't really know something about the internals, or you don't have a lot of information, at least, about the internals of the application you're testing. And predominantly, it has been used in modern fuzzers targeting crash or memory corruption bugs. So there we have cases of fuzzers that don't have any sort of expert knowledge, but they compete with domain-specific engines due to this evolutionary core that they have. So the question we asked, okay, can we steer evolutionary testing towards complexity bugs in particular? And something that directly becomes noticeable here is that coverage, which is usually used to drive evolutionary phases, is irrelevant in the case of complexity bugs. So if you think about an example of a loop that executes many more times than what it should be, in a modern fuzzer where you just go for coverage maximization, once you cover all the basic blocks and all the edges for that particular loop, then after a while, you've just explored everything. So here, the objective is to actually trigger this loop to execute many, many times until you hit this worst case performance that is unexpected because it's not your average case performance. But we also want to do it without throwing away the whole fuzzing infrastructure. So we're going to show you how we went about this and built this prototype fuzzer, where basically what we wanted to do was to maintain an input corpus, but drive it towards slower and slower executions. So essentially, we follow the traditional evolutionary testing approach. We start with an input corpus of some seeds, and what we do is we try to refine it by mutating these seeds. And we do so by getting some resource use information by the program, and then basically guiding again this corpus refinement process. So what we really want to tweak here is these three parameters to control this input generation. So these controls are the instrumentation, the fitness function, and the mutations. So essentially, we want a fitness function that will favor inputs that introduce slowdowns. And it's really important for us to have mutation operators with locality in mind. So what do I mean locality? So suppose you hit this case of an endless loop or an infinite loop, which is triggered because of a bug. Suppose you have an off by one error, and now somewhere in your application, you end up with an infinite loop. You don't want your fuzzer to start exploring different parts of the code, but you want to actually, once you find the loop that could have a complexity vulnerability, stay there and try to exercise these inputs more and more. And of course, you don't want to be getting stuck just at a single loop, right? So what we wanted to do, say if we wanted to just focus on the quicksort algorithm, we would like to start from an input and suppose we measure the number of instructions, and that's our measure of how slow our units are. We would mutate it, and we would see if our new instructions are more than our previous inputs. So the more we see that our inputs are causing slowdowns, we will continue mutating into that direction until we end up with an inversely sorted array, which is, of course, for a bad pivot selection, one case for a worst case input. So these are the key ideas for SlowFuzz. So we picked a very simple function that maximizes the CPU instructions, and we designed different mutation strategies to preserve that locality. So in the traditional scenario, what you do is you have a set of mutation operators to modify your inputs, and then you pick one of your mutations at random. In our case, we don't really want to do that because we want to have this locality property. So what we do is we insert some probabilistic attributes to our mutations. So with some probability, we will pick some mutations based on their success. So we could prioritize based on the offsets of the input that we want to mutate, or we could prioritize based on certain mutations that have been shown effective in that particular application. Or we could say for certain portions of the input, certain mutations are more effective. So we wanted to verify if this hypothesis is valid. And to do so, again, for the simple case of sorting, we implemented our toy examples of insertion sort and quicksort. So here, we implemented the algorithm so that we know which is the worst case performance. And we wanted to ask how far are we getting from the theoretical worst case using this evolutionary fuzzer. So here we have a graph depicting the insertion sort and quicksort implementations of ours. And the line in red is the theoretical worst case. And the dashed line in the bottom is the brute force attacks for these two cases. So we show that in both cases, we managed to get approximately at 85% of the theoretical worst case for this very simple problem. And this is because we know which is the worst case input. So we wanted to see what if we don't know what the worst case input is. So we tried on quicksort implementations in real world operating systems and from different open source communities. So we show that, for instance, we managed to achieve 3 times slowdown for a fixed input size for the quicksort implementations of Apple and the OpenBSD communities, 26% for GNU and 8% for the NetBSD. And this is without knowing what the pivot selection strategy is. So even for something very simple as that, theoretically reasoning about what is the worst input for a particular pivot selection it takes some effort, but we can see how we can easily modify the fuzzer to find these instances. So how do these engine properties actually affect the execution? For instance, what if we're using coverage instead of maximizing for CPU instructions? So for the simple case of OpenBSD, we see that, for instance, in our mutations, here we depict how big of a slowdown we get for the different mutation strategies. And you see here that if we just pick random mutations, at some point we hit a plateau, so we don't increase our slowdowns further. And if you think about why, it's because random mutations break this locality property. So for instance, suppose you have a sorted array, And at some point, you do a crossover operation. So you take two pieces of the array and you mix them together. That essentially breaks all your sorting. So you would want to penalize this mutation for that particular case. And of course, there is trade-offs depending on the different modes. And likewise, we see that coverage as a metric doesn't add anything because once you sort an array, essentially you've explored the whole program directly. And after a while, you cannot really guide the fuzzer to bring slower and slower inputs just by using coverage. And of course, there is no benefit into using some sort of time-based measurement instead of CPU instructions because of the noise simply. So we see that we would degrade our input generation if we used time instead of CPU instructions. So we're starting to see that evolutionary testing for complexity bugs is promising. So in this very simple scenario, we managed to get some promising results. But what about if we apply the same fuzzer with the exact same engine into common instances of complexity vulnerabilities that have been seen in the wild? For instance, what if we apply it on something harder like hash tables, where we have seen denial of service attacks due to collisions? So to answer this, we implemented, we stripped away the hash table implementation of PHP. So PHP utilizes the DJ Bernstein hash for its string hash when you have string keys for your array, and this is known to suffer from collision. So we know that, for instance, if you have two strings that consist of characters A, B, and C, D respectively, if you have the certain condition between the characters, then you will have a collision in your hash table. That basically means that the performance of your hash table will degrade to a linked list. So you won't be inserting into your hash table effectively. So basically, this is a well-known case of worst-case performance. And attackers have exploited that in the past because if you have two strings that collide, then if you select the same prefix and suffix for two strings that collide, you can create more and more strings that collide. So you can essentially increase these collisions. So what we did is we implemented a small hash table and we said, okay, let's allocate 64 entries and let's do at most 64 insertions and let the fuzzer pick the inputs on its own. So we show that SlowFuzz, with exactly the same engine that was finding slowdowns in a quicksort example, manages to find increasing number of collisions in the hash table. And this is basically without any knowledge of the internals of the hash function. So this is really critical because you could be given the hash function as a black box, and now you're starting to see these slowdowns. And if it is something that you don't want, it's an alarming thing. So we said, okay, how about we go to other cases of complexity vulnerabilities that have been exploited in the wild. And one notable example is, of course, regular expression denial of service attacks. So whenever we have regular expression matching, we have this problem of backtracking. So in cases where you have a regular expression to be matched against a certain string, it could be the cases that your regexes are what we call evil regexes. So they will cause an exponential or quadratic or superlinear in general slowdown on a given input once they are matched. And this is, of course, a hard problem, and there has been some work from the theory community to reason about the properties of regexes and which regexes are evil and what conditions should be met to have this behavior. And of course, it's really relying on the implementation as well. So the question we asked, can we take the exact same engine that we applied on the previous two problems and apply it in this case of complexity vulnerabilities? So if we have our fuzzer and we have a fixed input, will SlowFuzz generate an evil regex for that particular input? And that is, we found out that yes, it can, without knowing anything about what the regex looks like or what is a valid structure. So here are some examples of regexes that are generated by SlowFuzz on a fixed input. And essentially what we have here is we could have exponential matching for a given regex. So to give you an example, suppose we take this simple regular expression b plus c. So here, this is a regular expression that matches any string that starts with a b and then is followed by any number of b's ending with a c. So here, if you have this as a backtracking problem, then you have exponential matching. And the reason is that in order to reach this accepting state Q2, suppose you consume two Bs and then C. There's two ways to reach that particular state. So either you could go Q0, Q1, and then Q2 directly, or you could go Q0, Q1, and then Q1 again and Q2. And in both paths, you're consuming the exact characters. So the fuzzer does not know anything about this. All the fuzzer knows is it's using this fitness function to go for more and more slowdowns and the mutations to preserve that locality property. But we see that in the experiments that we run, it manages to consistently generate regexes that cause a slowdown. So this graph depicts an experiment where we have 100 runs, and in each run, we let the fuzzer run for 1 million generations. And that is very fast, so it doesn't even take more than 10 minutes. So we ask it to generate regexes of 10 characters or less, and we see that with 90% probability, it will generate at least 31 regexes that cause a slowdown, and at least 2 regexes with superlinear matching. And about half the cases will generate the regex with exponential matching. And this is again the same engine that generated the collisions in the PHP hash tables, as well as the sorting slowdowns. So of course, one question which is logical is, okay, what if we now have a certain fixed regex, and now we want to find an input that triggers a slowdown? So for that, we harvested regexes from deployed web application firewalls. So these are regexes that are not supposed to suffer from slowdowns, especially exponential or quadratic slowdowns. And we show that we can find slowdowns from 8 to 25%, and there's different patterns where you can see this increase occurring. So again, even in state-of-the-art libraries like PCRE and regexes that are deployed in the wild, we can get slowdowns on this. Finally, we wanted to evaluate SlowFuzz on performance-sensitive applications such as compression and decompression binaries. So what we did is we applied SlowFuzz on bzip, and we asked it to basically generate inputs of at most 250 bytes and observe what are the decompression times. So again, without any changes into the internals, we see that after a few hours of fuzzing, we managed to achieve more than a 300 times slowdown on a fixed input size. So again, this is without any modification on the engine, without any knowledge of the internals. So essentially, the key takeaway from this talk is that we make the case for automated detection of complexity bugs through fuzzing, and we show that this is possible in non-trivial scenarios for several instances of complexity vulnerabilities that have been seen in the wild. And I guess the key takeaway is that evolutionary testing should be seen more as a generic means of code exploration. So different bug types have different objectives, and we should adapt modern fuzzers to go beyond the code coverage maximization and basically design new instrumentation routines and fitness function to particularly serve our given objectives. So essentially, we have one objective and different controls, and we can tweak them to our needs. And with that, I'm happy to take questions.
Hi there, Will Robertson, Northeastern. I really like this work. I really like this observation that there's a different or potentially more objective functions than just coverage. But I'm wondering, can you talk about like the maximum size of the artifacts that you looked at? Because it sounds like you were pulling a lot of kind of small, constrained, well-defined pieces of code out of applications, and so if you're trying to find this in a larger application where you may not know where the complexity is, right, in some sense.
Yes.
Coverage might actually be something that you do want until you find something that looks complex, and then you kind of dive into that, like, switching objective functions, right?
Exactly. So that's an excellent question. So essentially, if you notice, of course, we have a very constrained set here of experiments, right? So the idea here is it's twofold. First, this can be used orthogonally to other fuzzing techniques, and of course, there is plenty of work that is doing static analysis, particularly for this kind of bugs. But with respect to the inputs, for instance, right, there are several cases in which you have some sort of complexity bug, And that should be a fundamental property of either the implementation or the algorithm. So it doesn't really matter if your byte, if your input is 64 bytes or if it's 128, you should still be able to see the same relative increase in the slowdown. And of course, there are several cases where you cannot reach it. So you cannot, for instance, take that, run it in Chrome and directly find the spots where you have these vulnerabilities. But I guess in this work, what we mainly wanted to see was to evaluate this technique in what we know of as the most prevalent cases of complexity bugs. So we wanted to verify that this is the case, and of course, there is lots of room for related work and future work on this.
Absolutely, yeah. So just to be clear, then you see this is kind of being composed with some other technique that does maximize coverage.
Yes.
Okay.
So it's basically a fundamental. It's a stage that this is doable. We should explore this more. And it's a first step towards that direction.
Yeah, awesome. Thanks.
Hi, thanks for your presentation, Abhi Krochudru from NUS. So there is a lot of work on finding worst case execution time, where also you need to find the worst case input sometimes.
Yes.
So the main difficulty in that line of work is the infeasible path detection. So if you need very sophisticated infeasible path detection mechanisms amounting to symbolic execution, then of course it goes out of the window. But if for your example, simple infeasible path detections would suffice, then finding the worst case input, or as you have defined it, just the one with the maximum number of instructions, is not very difficult. It's quite scalable.
So,
and it seemed like that from the examples given. It seemed like that a program analysis approach would be sufficient. So it's more like a comment. This is for you to consider, I guess.
So actually thank you for the question. So I think there is a benefit into following both approaches.
Okay.
And the reason I'm drawing on this is the example of fuzzers, right? So fuzzers are inherently dumb, yet they perform really well.
Yeah.
So you have very sophisticated passes on that. But on the other hand, we have evolved fuzzers over the years towards finding these crash-inducing bugs. They're not really generally thought of as this tool that could be explored towards other classes of bugs. So
there I differ a little bit. There is this huge area of search-based software testing where this multi-objective searches have been looked into, just not in the context of AFL.
Yes, of course.
But they have been looked into. But I take your point that that's different approach from program analysis.
And of course, these techniques are generally orthogonal, right? So you can combine.
You can certainly combine. So it's quite possible one of the outcomes from your presentation can be that somebody takes AFL and kind of starts looking at multiple objectives on top of AFL. It wouldn't be very hard to implement based on the experience in the search-based software testing community.
Thank you.